Okay, let's get started. So first of all, thank you so much about last night. That test is really important to us. So I really appreciate. It seemed like everybody was working on it. I felt kind of bad not letting you leave. Felt kind of like a cop or something, right? But again, it's just that in rooms like these, when people start leaving early, and with a test like that, people have a wide range of how long it takes them. And so it just gets super chaotic and super distractive. So anyway, thank you so much. I appreciate that. Also, thank you so much for being my first class here at UCSD. I really appreciate it. I had a lot of fun. I really, from like your PCQs and stuff, hey, thank you. Thank you. From your PCQs and stuff, I can tell you guys really tried, so I really had a lot of fun. So let's do one last lecture. So these last two lectures, I sort of set them up. So we're talking about new stuff, but there's a lot of old stuff in it. So hopefully you saw that last time, and this time will be the same. So it's kind of a good review. And sort of my thing is, I'll give you homework problems for these, but basically these last two lectures, if there's something on the final, which there might be, it'll be something sort of easier and something like the stuff directly like stuff we did in lecture. Okay, so it wouldn't be, again on a test or something, you'd have sort of hard problems and medium and easy, and so it would probably be more like an easy type stuff from here. But it's, anyway, so let's move on. If you have any questions, let me know. So the last thing we're going to talk about is the last circuit element that we're going to see, or that you pretty much will ever see in first year physics, which is an inductor. Now, and an inductor, it's one of those cases where it's just, for some reason, we find a way to name things 8 different ways, right? So inductor is literally just a solenoid, okay? And sort of it's, the word inductor is sort of how we use it. But it's literally just a solenoid, and a solenoid is really a fancy way of saying I wrapped a bunch of wires around something, okay? So it's just literally a coil of wire. And as we've been seeing with Faraday's law, all right, when you have a current going through that solenoid, right, if the current is changing, there's going to be an induced EMF. And that's what the whole sort of idea of an inductor is. Okay, so it's a coil of wire. And by inductance, we mean that it's sort of designed to induct, to induce an EMF or induce a current. And so we're going to sort of talk about how that works and how that might work in a circuit leading to the idea of AC circuits. And so we define the inductance of a solenoid with this letter L. And this letter L, the definition is just the magnetic flux, which we know a lot about, divided by the current. The unit for an inductor is Henry. So here's 1 Henry. And a coil of wire, again, is used in a circuit as an inductor. And so you can use this, as we'll see, for different reasons. And then the circuit symbol for this is usually just a little curly-Q thing like here. And so if we sort of look at this and just try to understand this definition. So basically, the idea of an inductance is sort of how much magnetic flux you have per current. And so for our solenoid, right, if we write out our magnetic flux, that's BA. Now I'm going to assume, like with a solenoid, which is always the case, that our magnetic field is along the same axis. So we have our solenoid like this, and so our magnetic field is here, and so that's in general going to be parallel with the area vector for our loops. And so that cosine thing goes away. And then the other thing is, so this is the magnetic flux for one loop, and since in a solenoid we have a number of loops, we'll put an N in there. So MBA, if you remember, I'm from, or at least I just came from Toronto, so MBA is kind of a fun thing for me right now, if you're into that. And so the magnetic field for our solenoid is N, and then here we're going to use lowercase l, because we have this big L, times current divided by area. So when we define this inductance, it looks like this here. So it's this thing divided by I, so I get, something like we had in that last picture, mu naught n squared divided by L times A. So just like what we have in this picture over here. And so again, it's sort of your inductance, again, is a measure sort of how much EMF you're going to induce depending on sort of, per current. And so it's, your magnetic flux divided by I. Okay, and so here's a picture. Again, we've seen pictures of these. We called them solenoids before. Now we call them inductors. And so when there's a current going through the inductor, a steady state current, a current that's not changing, it's really boring. Okay, it doesn't really do much. It makes a magnetic field, okay, but it doesn't really do much as far as in the circuit. It's just, and you might even make one by accident by sort of curling up your wires if you're doing a current. But what's going to be interesting is cases where we have the current either increasing or decreasing. All right, and we know what's going to happen is that we're going to create an induced current that's going to try to, sort of go against that change. And so down here, we have the voltage, okay, across an inductor. And so it looks like the inductance L times di dt. And so that's, again, the change in the current. So you only have a voltage, right, across this when there is some change in the current. And this is literally just this same idea that we've been dealing with here of an induced EMF. Okay, so when the current changes, your magnetic field changes, you have an induced EMF which makes a current. And so if you look at this one here, so this is where we're kind of reviewing. And so in this case, our current is going up this way. All right, and we say that it's increasing current. So the current's going up, and so it increases, all right? And if you remember from the picture before, okay, when our current's going up, so let's all do our right-hand rule. If our current's going up nice and steady, the magnetic field for this inductor points this way, okay? So if you sort of follow your hand along these curly cues here, okay, it points that way. And so what happens here is, in this case, so the current's coming up this way, and so if you're increasing your current, that means your magnetic flux pointing to the left is increasing, so you want to induce a magnetic field going the other way to counteract that. And if you look at how that current would be going, that current is going in a direction that opposes this current. And it's going in a way, so in a sense, what you're doing is you're sort of creating something that's going to sort of send current that way. And so this would be our positive end, and this would be our negative end, okay? And so here, increasing current, so you see the sign from this equation, increasing current, if it's positive, then this is a negative. So as your current goes through here, the voltage drops. So we have the same positive and negatives that we would have used for resistors. And just to kind of show you that this is like really just the kind of stuff that we've been dealing with. So, remember that our EMF, our Faraday's law, was something like this. It was N times the change in the magnetic flux with respect to time. And so for us, there'd be an N. And what is our magnetic flux? Well, it's the B field times the area. So for our solenoid, that's N divided by L times mu naught times the current times A. And of course, it's the derivative of all this stuff. And if we go through and do that, we get mu naught, and again, there should be an N outside because there's many loops there. So this is, the induced EMF for one loop, and since there's many loops in a solenoid, there's a bunch of those. And so we end up with this sort of same thing we had before, mu naught N squared A over L, which we again call the inductance, and then times di dt, all right? And so we could have sort of asked you to calculate this from previous knowledge that you were doing, okay? And in fact, we probably had problems where you actually had to calculate this very almost same thing. Okay, so this really is just Faraday's law, just sort of written in a slightly different way. And then on the other side, okay, what happens is we get, if we have the current going this way but it's decreasing, then you want to create a magnetic field going that way, all right, with the magnetic field to sort of keep it the same. And in that case, your current is sort of going this way, which has a sort of sense of a negative there and a positive there. Okay, so the induced current carries positive charges to the right. And so in here, this would be negative. The negative signs would cancel, and then your voltage would be a positive. So again, with our sort of signage, as I come through here, if I come in at negative and come out at positive, I'm increasing my potential, my voltage, so it's a positive thing. And so this is our voltage for the inductor. And so this is just kind of a little sheet that summarizes that. So if you remember, when we did this for resistors, if the current was coming this way, we modeled it this way, which to us meant that when the current came in, the potential decreased. Okay, so our potential was decreasing through here. And it's the same idea in this case here. We got this negative sign, and so if DI is positive, then this will be a decrease, which means the sort of EMF is pushing the other way. And if this is negative, those signs switch there. Okay, so that can be a handy thing. And so let's try a question here. So which current is changing more rapidly? And then just as a hint here, we'll say that we have this new equation that says our potential equals L times di dt. Okay, so, and we give you information. So there's two inductors. We tell you the inductance, which is the 2 Henry and the 1 Henry, and then we're telling you the voltage across them, and we want to know is which one has a bigger magnitude change of current. So think about this one and let us know what you come up with. Okay, and it looks like we're doing pretty good. We're just learning this stuff, so that's great. So I think I agree with the majority. And so if you use that equation, what I would do is just invert it and say, okay, well that means my change in my current is going to be equal to whatever my voltage is divided by L. And so in case 1, di dt would equal voltage, 2 volts over 2 henries, and that comes out to be 1 amps per second. And then in case 2, if I do that, I get 4 volts divided by 1 henries and 4 amps per seconds. Okay, good job. So we got that. It's just kind of getting kind of a picture of this. All right, so now we're going to look at this in a circuit, just like we did with capacitors. So there'll be some sort of analogies to this with capacitors. So what you can often do is set this up. Here's a nice DC battery with your resistor and your inductor. And what we can do is go through, okay, so let's say that we start our conventional current like this. If I do my signage, I'll get a positive and negative there, positive, negative there, and then positive, negative there. So again, the current is sort of just starting out, we'll say. And so if I do this, okay, over here, I get, so let's just do a Kirchhoff's rule. If I start here, I come this way, I get a positive voltage. I get a negative L times di dt, and you know this, just to be precise, this should be a derivative. So this should be like d dt, not a delta. Apologies there. And then I come this way, and I get a negative IR. Okay, so the equation I get by using Kirchhoff's law looks like this here. And so we can go through and interpret this equation a couple different ways. So we'll sort of deal with the one later. But one thing that we can do is just say, okay, well, this whole thing here is my voltage over the inductor. And so I can take that and solve that equation just for my current. And we did a similar thing when we talked about RC circuits. And so the current is going to look like this here. So at initial time, all right, when the current, so what's going to happen here is your current's going to start out, and what the inductor does is the inductor doesn't like any changes in current. So when the current starts out, the inductor is going to just sort of push against it and stop the current. That's how it works, okay? So the inductor, if your current is sort of increasing coming through, it's going to work against it to stop it. And if it's got current in it, and it wants to, and you cut off that current, it's going to sort of try to keep that current going. So it always works to change what's happening to you. And so what happens is at time 0, okay, the voltage in the inductor is high, and so your current starts out at 0. And then later on, as your current settles down, okay, the current will go up to your maximum amount. And so what happens is this essentially sort of works the opposite the way a capacitor did. All right, so initially, these questions where you ask what happens at time 0, what happens later on. Initially, the current is 0 through the inductor, and so the inductor basically blocks all current through it. Okay, so it's kind of like there's a block in that part of the wire, and then at some later time, the inductor acts just like a wire. Okay, and so what we can do is and then this is what it would look like. Okay, the actual sort of graph of this. So what happens is the inductor again starts fighting off the current, and then the current rises up and eventually reaches some value. Okay, this is the case of this one here where you have just one resistor and one inductor. So initially the inductor fights your current, stops it completely, and then as time goes on, it can't sort of fight it forever, and it basically settles down, and then at the end it's just like a piece of wire. It's a curly piece of wire. It'll have a magnetic field in there, but it won't be adjusting your current. And so your current will eventually end up with the point of your battery's voltage divided by that resistance. Okay? And so that's what will happen in a RL circuit. And so then what we can do is look at something like this and interpret it similar to how we would have interpreted a capacitance circuit. So again, at time 0, this thing blocks current. Later on, it lets all current through. And so here, what will the power drawn from this battery be initially right after the circuit is connected? And so this is, again, some practice with circuits as well as sort of this new stuff here. So discuss this with your neighbors and see what you think. Okay, so I think we've thought about this, and I'm happy with our results. So we got this here. So let's look at this. So this is a situation again where, so at time 0, this just blocks all current. Okay, so this inductor sort of behaves like there was just like a blank here. Okay, and so it doesn't actually let any current through, and so what I always do is I like to kind of go through and redraw the circuits. And so in this case, it would end up being a circuit like this, with just 2 resistors that would be in series. So initially, no current will go down that path with the inductor. It's going to fight it off. And so then, what do we got to do? Well, this is a little bit trickier, so this is good. So the power drawn from the battery is the current times the voltage. So the voltage, you know, is just V, and so we got to find the current. Well, in this case, that's not too bad. The current in this circuit, you know, if you broke this one down to, you know, the simplest circuit in the world, like we like to do, it'd be V over 2R. And so the current would be V over 2R. So I plug that in over here, and that gives me V squared over 2R would be the current initially after this thing goes. Now, just to ask ourselves, what would happen in this case if I said, okay, what about some long time afterwards? What would happen then? Anybody got an idea? Like, what would happen to the inductor?
So the inductor would act like a normal wire, and therefore it would short circuit the R that's parallel with it, and just have the resistor break off.
Exactly. So that's exactly right. So this is good too to say that unless we say otherwise, you assume the inductor is a wire with essentially very, very small resistance. And so at a long time later, that L would just be like a wire that would short circuit that R, okay? And then you just would have the circuit with the V and the R some long time later, okay? So again, you can interpret sort of the long time before and the long time after with more complicated circuits by sort of thinking in this way. Questions, anybody? Question then here.
So you said like initially it's not going to go through L, but like long time after it's going to short circuit, right?
Yeah.
Halfway through, is it going to flow through both?
Yeah. It'll sort of have. It'll go through both. Yeah. Okay. All right. And then back to that. So again, so lots of time there. Any other just logistic style questions? Then I'm going to start posting your grades for everything. And so just like with the quizzes, if you notice that your grade isn't right, let me know. If you opted out of discussions, your discussion grade will, probably be a 0 if you didn't go. But I know, to adjust that. So I mean, there's no mechanism for me to sort of, give you perfect discussions. I don't know what your final exam grade is yet. But just, don't worry about that. But we have it written down somewhere. And the other thing is when you start seeing these grades, let me know if you've got issues, and we'll try to take care of them as we see them. Okay, so no more logistics. So the last thing, this is my last chance to kind of plug the course evaluations. So we got a pretty good response rate so far, but again, for me, the more the merrier. So the more voices I hear, the better. Especially with it being my first time at UCSD, I'd love to hear your opinions about stuff, how things went. This is also what the higher ups look at when they start talking about your teaching. So it's also nice things to have that in there. So my idea was we didn't have PCQs this week. Hopefully that frees you up a little bit. Maybe you could find that time to do that. I know you're super busy right now. Okay. Any other logistics questions? All right. So here's you can't read it, but this is the signs you've taken too many classes with Dr. M, right? And one might be too many, right? We'll sort of see. Okay, so you probably got a little bit too into March Madness, right? That can be a sign. You can only communicate in clicker question format to other people, right? You start making top 10 lists for your cats at home. Notice the guy at the mall with a huge head and you burst into tears. Find yourself streaming more Christopher Walken movies than usual, right? Why am I watching so many Christopher Walken movies? You start calling everyone you know yo physics. That's another thing, right? And then you cut your hair like this, right? That's the most dangerous sign, right? If you do that, you need to seek help, right? Okay, and so now here it is. We've been waiting for this all semester. I don't know what to think. Okay. Vote now or forever hold your peace. We're going to call time. All right. Anyone want to guess? SpongeBob by a landslide. Man. Wow. Yeah. What a I mean, what a Cinderella story. I don't think a third seed has ever won this before, so that's really exciting. Yeah. All right. All right. So another thing, so we talked about this, that a capacitor can store energy, and the way we kind of thought about that is what a capacitor does is it takes positive and negative charges and separates them, and then that creates energy when you do that. There's like a potential energy, but you can also think that there's energy stored in that electric field. Well, but by the same manner, okay, an inductor can store energy, and it stores energy when there's a current in it, right? Which makes sense. When there's a current in it, it's making a magnetic field. Okay, so we can store energy in electric fields or in magnetic fields. And so the last thing then we're going to talk about is kind of related to this is LC circuit. And so this is an example of a circuit that's going to oscillate, which is, this idea of like an alternating current circuit. So it'll be oscillate in a similar way to like an AC circuit would oscillate. And so we set up a capacitor and an inductor. And so we're going to go through and look at this a little bit. And so we're going to assume that our capacitor is like fully charged. That's the sort of situation we're going to deal with. So we assume that our capacitor is fully charged, and there's a switch open, and then we're going to close this switch and try to see what happens. Okay, and how does the circuit respond? Well, what's going to happen is the charge and the current are going to oscillate. So this will be an oscillator, and we're going to show that it's very analogous to a mass on a spring, which is something you probably talked about in 2A at length, right? And so, again, what we can do is look at this, and whenever we have a complicated circuit, the easiest way to kind of look at it is using Kirchhoff's rules. Okay, so we're going to assume that when we close this switch, there's going to be a current. The positive charges will start to want to flow to the negative side. And as they do this, they're going to be causing a voltage in your inductor. And so what we can do then is go through and do Kirchhoff's rules. And so what I'll do is to do that, I'll start down here, and I'll go, from that point, I'll go counterclockwise. And so when I do that, I get negative L di dt, that's the voltage across the inductor, and then plus Q over C, that's the voltage across the capacitor, and that equals 0. So according to Kirchhoff's rules, those two, this will be the sum of our voltages, and those should add up to equal 0. And so typically, when you get to these more complicated circuits like this, then what you do is you try to break these down into a differential equation. So this is probably real similar to stuff you did, again, with a mass on a spring. So the first thing we're going to say is that the current, okay, is going to be negative dq over dt. And the reason it's negative is because your charge is going to be leaving, okay, that capacitor. And so when we talk about Q is how much charge is on that capacitor. So in this case, as the current moves from away from here, you're going to be reducing that Q, okay? And so it might be good to kind of just sort of define that our Q for us is going to be the charge on the top of the capacitor. It'll mirror what happens to the one on the bottom, but we're going to call that there. And what I can do is say, well, then di dt is equal to negative d squared, so the second derivative of q with respect to t. And so if I take this equation here and clean it up a little bit, I get L d squared q plus q over c. And so again, I don't know if you've seen much of these things, but this is a differential equation, which is like a super important thing to us people in STEM and in the STEM field, right? And so our goal here, so we have this Q as a function of T. So this equation gives us a recipe to find out how the charge on the capacitor changes with time. All right, and so you'll go at some point, probably most of you, and take a differential equations class if you haven't already, and that teaches you to go through and sort of solve these differential equations. Now, what's nice is that in general, if you can sort of guess the answer, that works as well. And so here, I'm just rearranging this to kind of make it a little bit more illustrative. And so this is kind of your classic differential equation, if you will, in physics. Okay, so if I just brought the QC term over and then divided by the L, and then just realizing that the L and the C are constants, so I'll put them over there. And so this is my differential equation. So what this is telling me, okay, is I want to find some function Q of T, where if I take two derivatives of it, I get back the exact same function times a negative constant. Okay, so that's how I would think about this. Now again, you'll learn more eloquent ways to do this in differential equations, but I think this is a good way to think about it too. So does anybody know what kind of a function, if I take two derivatives of it, it gives me basically negative of some constant times itself? Anybody? What's that? Okay, so I'm hearing oscillating, sine, cosine. So these are all correct, some sort of sinusoidal function. Now, what I'm going to do is just kind of make a general case. So our sort of general solution can be written, lots of ways, but I'll write it this way here as cosine omega t plus phi. And so these are all kind of unknowns. And then the way that then you do this is you can go through and solve for those unknowns using your initial conditions. But now for us, what does this mean for us? And so first of all, I'd like to say, so we're starting out at the time when Q is maximum. And so I'm just going to write my cosine function like this here. Okay, so this is my Q of T. So at time 0, I'm going to have the maximum value of my charge. And then what I can do is take a few derivatives. So here's Q prime of T. If I do that, I get negative omega A sine omega T. And if I take two derivatives of that, I get negative omega squared A times cosine omega T. And so here's what I was talking about last time. Okay, so if we write the equation this way here, which is a nice way to write it, and then I plug in for that, so my second derivative with respect to time would be negative omega squared A cosine omega T, and then that equals negative 1 over LC times my actual charge, which is A cosine omega T. And so I did, like you guys said, we did exactly what we wanted. So we got this equation here. If I take two derivatives of it, I just get some negative constant times itself. And in this equation over here, I've got basically the term A cosine omega T on both sides. And so I can cancel that out like this and like this. And I get this important relationship here that tells you, so again, to unpack all this stuff, because this is kind of mathy. So we're starting with Kirchhoff's rule. We showed that basically the charge is going to be an oscillatory function. It's going to be a sine function. It's going to oscillate. And better than that, we found that the oscillation frequency is 1 over radical L times C. Okay, by going through and doing this here. Anybody got a question? Like I said, you probably did this in 2A. I do think this is the kind of thing that's good to see a couple times before it really starts to hit home. And then when you do differential equations classes, you'll learn ways to deal with ones that are trickier than this. This is sort of our basic differential equation, if you will, I think. Okay, and so here's how this would look. So here's our sort of pictures here. Okay, and so here would be the charge on the capacitor as a function of time. All right, we know that that's here, so we'll call that this thing here to be Q0. That's the charge at time 0. If I plug in time 0, I get 1, and so that's the maximum. And then the current through the inductor is I max times sine omega t. And again, one thing to be kind of conscious of is the fact that we're defining our current to be negative dq dt. So that's why this works out this way. But we can kind of look at this picture and then just kind of try to interpret this. It's always good, especially when there's so much math, to kind of think of this physically. So what happens is at time 0, right, you've got this circuit that wants to start sending its positive charges around. Okay, so it starts decreasing Q, but this inductor does not like that, and it basically fights it off. Okay, it keeps the current really small at first, and then the current, again, the inductor can't fight it. It can't always fight it, so it just sort of fights it at first, and then finally rises up. And then what happens is when the charge on the capacitor is 0. Okay, so when the capacitor is discharged all of its charge, which in a RC circuit it would be done at that point, in a capacitor and resistor. What's happening is at that point you've got this current in the inductor, and that current can't just stop immediately. Okay, so that current keeps on going in such a way that it charges the capacitor the other way. Okay, so the capacitor started with positive charges on the top, and then it'll end up with negative charges on the top as it sort of charges itself in the other way. And then basically this thing just repeats. And again, what we generally, with this kind of a topic, we try to remind you of the analogies to the stuff you might have talked about in 2A. So it's sort of like a spring and a block. Okay, so you can think about if you stretch a block to some points, this is like the equilibrium position of the block. If you stretch it out over here and let go, that's kind of like the charged capacitor. So the capacitor is charged. It wants to start making current, okay? And then what happens is at some intermediate point, okay, the block is pulled here. You got the maximum velocity of the block. This spring is now starting to push back. And so here, the current has gone through. All the positives have canceled out these negatives, and so the capacitor is neutral. But again, you've got this current in the inductor, and the inductor cannot just stop. Okay, and so the current continues on to the point where you then flip the signage of the capacitor, and that's sort of like this block comes over here and stops. Okay, so sort of velocity equals 0. In this case, it's sort of like current equals 0. And then this thing basically just happens again. So now these positives want to go over to here, and they do it. And again, when they, discharge the capacitor so it's neutral, there's still a magnetic field here that doesn't want to stop. And so you get this oscillation back and forth. Okay, so sort of a mathematical explanation and hopefully a conceptual explanation. But then let's look at some results of this. So here's a kind of, yeah. Well, here, let's just answer it for kicks. Why not? So the idea here is that, so we're saying in this first case, okay, the frequency is 1,000 hertz. Okay, so the frequency that we use in this case over here is 1,000 hertz. And so we want to know is what's the frequency in the other case? And so basically, one of the tricky parts here is that frequency and omega. And it's just one of these things that I know when you first learn this, it can be tricky. But we give omega. And why do we give omega? Well, because omega is what's inside our cosine and sine function. And so it's sort of what pops out naturally from our equations, right? But in reality, what we want to do here is in this problem, they're forcing you to kind of think about this in terms of frequency. And so the way I would think about this is, okay, so in the top circuit, it's 1,000. So we know that omega is equal to 1 over radical LC, and that's in the first case. Now, in the second case, how does the capacitance change? We got two capacitors in series, okay? And so if I'm doing two capacitors in series, I'm going to take the equivalent capacitance like this, and this is one that we did a lot, okay? When you got two identical capacitors in series, just like if you have two resistors in parallel, and you add those up, okay, the equivalent becomes C divided by 2. And so what's really happening is if I call omega 1 to be 1 over LC, like so, then my omega 2 will be 1 over radical LC divided by 2. Okay, so the actual value of that capacitance is C divided by 2, which, if you clean this up, will end up being 1 over radical 2 times radical LC. And another way to say that is it will be radical 2 times my initial omega. And so omega and F are off by a factor of 2 pi, but the thing is I don't really care about that because I'm asking about how they relate to each other. So basically, the second one will be radical 2 times the first one. If you take radical 2 times the first one, you get this answer of 1400 hertz. Okay? And so this angular frequency is the kind of thing that you really want to remember because this is a useful thing for a circuit like this. All right? And so here's basically any kind of thing that accepts radio signals, okay, any kind of communications device, that kind of thing. What happens is basically there's all these kinds of signals all over the place with different frequencies. And if you have an LC circuit, okay, it's sort of just like when we talked about the idea of resonance, when you, again, back in 2A, when you talked about this kind of stuff. These circuits, if you try to drive them with some frequency that's not close to their resonant frequency, okay, which is this one we just found, you're not going to get much current. Okay, so these circuits really are such that they want to accept this special kind of frequency. All right, and so if you're building something like a cell phone that you want to only accept certain kinds of frequencies and basically block all the other noise out, okay, one way to do it is to have an LC circuit, okay, because again, it's a really finely tuned circuit that only allows, or at least that sort of strongly prefers oscillations right around that angular frequency there, okay? Questions on that? So that's definitely the one thing you, for sure, I would say, want to remember about this stuff. Okay, I'll be down here if you got questions.